This training module is an overview of methods for modeling concentration reductions by BMPs. This is training module 9.04 for the Stochastic Empirical Loading and Dilution model SELDM. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 8 slides and will take about 8 minutes. This training module has 5 learning objectives. At the end of this module, you should be able to name the 6 concentration reduction processes, describe the 3 processes that may increase concentrations, describe the SELDM approach for modeling concentration reductions, discuss the minimum irreducible concentration, and describe the benefits of SELDM modeling for planning level analyses. Concentration reduction methods are physical, chemical, and biological. This diagram shows a source area on the left, a BMP in the center, an overflow or bypass route above the BMP, and the receiving water on the right. The flow terms are shown in blue and the concentration terms are shown as yellow. The loads are the product of the flows and concentrations. Concentration reduction mechanisms include settling, filtration, adsorption, volatilization, flotation, and various biological mechanisms including uptake, conversion, and degradation. It is commonly assumed that bypass flows and overflows are not treated. Outflow concentrations can be greater than inflow concentrations if previously stored constituents are scoured from the BMP, if there is carryover, or if the chemical or biological reactions convert or generate a water quality constituent. This graph shows the fitted cumulative distribution functions, CDF, for the trapezoidal distributions for suspended sediment concentration reductions at 17 swale monitoring sites and the distribution that would occur if the median of each statistic were selected. There are large variations among the distributions among sites in all the categories. The vertical axis is the concentration reduction ratio on a linear scale. The horizontal axis is a probability scale indicating the percentage of storms with concentration reductions that are less than or equal to a given value. The maximum values range from 0.4 to more than 3 times the inflow concentrations. The medians of the best fit statistics are 0 for the minimum, 0 for the lower and the upper bound of the most probable value, and 1.545 for the maximum value. This is a right-skewed triangular distribution. The minimum irreducible concentration, MIC, or MIC, is commonly defined as either the lowest concentration that can be achieved by a BMP or the background concentration. This graph is a yellow box plot showing the literature values for different constituents and a blue dot and line plot showing the MIC values calculated from the International BMP database values as blue lines. The horizontal axis shows the water quality constituents and associated concentration units. TSS is total suspended solids, TN is total nitrogen, TP is total phosphorus, DP is dissolved phosphorus, TCU is total copper, TPB is total lead, TZN is total zinc, FC is fecal coliforms, MPN is most probable number. On the box plots of literature values, the triangles denote the minimum and maximum values, the lines denote the 10th and 90th percentile, the box denotes the 25th and 75th percentiles, and the horizontal line denotes the median. The average is the white circle. The MIC1 is the 25th percentile of MICs for each category. The line on the blue dot and line plot shows the range of calculated MIC1 values, and the blue circle denotes the median of the values calculated from the International BMP database. The graph indicates that different MICs range over 1 or more orders of magnitude. Concentration reduction ratios and the MIC define BMP outflow concentrations. This graph shows the concentration of total phosphorus in highway runoff and outflows from a grassy swale and a detention pond BMP. This graph has a log scale on the vertical axis and the percentage of storms equaling or exceeding a given concentration with a probability scale on the horizontal axis. Highway runoff was simulated by using SELDM with statistics from USGS Scientific Investigation Report 2009-5269, which documents highway runoff quality at sites in Massachusetts. Swale outflow concentrations are higher than highway runoff concentrations in about 70% of storms because the grassy swale can be a source of nutrients from plant matter. Pond concentrations are greater than runoff in about 10% of storms because the MIC was estimated to be 0.3 milligrams per liter. In comparison, the MIC for the swale is 0.01 milligrams per liter. Because SELDM replaces concentrations below the MIC with MIC values, these values appear as the horizontal row of outflow concentrations on the right side of the plot. The two horizontal lines on this graph are current or historic water quality guidelines for total phosphorus. The upper black line at 0.5 milligrams per liter was a commonly used wastewater effluent limit. About 1.74% of highway runoff and 0.8% of swale effluent concentrations in this simulation are above the 0.5 milligram per liter threshold. None of the pond discharge concentrations exceed this value. The gray line at 0.1 milligrams per liter is a historic water quality guideline for total phosphorus in running waters. About 50% of highway runoff and swale concentrations and about 30% of pond effluent concentrations in this simulation are above this receiving water threshold. This graph indicates that ponds reduce high concentrations but not low concentrations, and swales are not as effective as ponds for reducing concentrations except at the low end. This example shows how SELDM can be used to evaluate different BMPs for meeting water quality criteria. Although the swale did not substantially reduce concentrations, both the swale and the pond are effective at reducing loads. This graph shows the loads of total phosphorus in highway runoff and outflow concentrations from a grassy swale and a detention pond BMP. This graph has a log scale on the vertical axis and the percentage of storms equaling or exceeding a given load with a probability scale on the horizontal axis. The graph shows that the pond is more effective at reducing loads for most storms, mainly because the pond is much more effective than the swale for reducing concentrations. This example shows how SELDM can be used to evaluate different BMPs for meeting load reduction objectives in TMDL studies. In this training module, we learn that concentration reduction mechanisms include settling, filtration, adsorption, volatilization, flotation, and various biological mechanisms including uptake, conversion, and degradation. Storm-to-storm carryover, scour, and biological or chemical conversions can increase concentrations of a constituent in BMP outflows. The minimum irreducible concentration is either the lowest achievable concentration or the local background concentration. And SELDM can be used to explore and demonstrate the potential effects of concentration and load reductions from different BMP designs.